Hello children, today we are going to discuss the general features of transition metal or transition metal chemistry. General features of transition metals. As we all know, transition metals के जो specialized कुछ specific properties होती है like variable oxidation state, complex ion formation, colored ions and catalytic activity. You will remember that when you are building the periodic table and working out where to put the electrons, something odd happens after argon. At argon, the 3s and 3p levels are full, but rather than fill up the 3d levels next, the 4s level fills instead to give potassium and then calcium. Only after that do the 3d level fill. The elements in the periodic table which correspond to the D sublevel filling are called D block element. The first row of these is shown in the shortened form of the periodic table. You can see S block and P block are in the side and D block in between the first row of D block element. Now electronic configuration, if we talk about electronic configuration of D block of 3D transition series, this starts from scandium and ends with zinc. Now you can see कि सब में आपके 4s2 इलेक्ट्रॉन है with few exception. सिर्फ आपके क्रोमियम और आप देख रहे हो कोबाल्ट, ये दो ऐसे हैं जिसमें 4s1 है. Why this happens? Because of 3D subcell is half filled in chromium and in copper 3D subcells is completely filled. Because of half filled and completely filled orbital, as we are knowing, half filled and completely filled orbital are more stable. That is why electrons shift from 4s orbital to 3D orbital. Not all D block element count as transition element. जिनके d orbital incompletely filled हैं, only those are known as transition metals. On the basis of these definitions, scandium and zinc do not count as transition elements, even though they are the members of D block element. Zinc has electronic configuration 3d10 4s2. When it forms ion, it always loses 2 4s electron to give 2 plus ion. With electronic structure 3d10, the zinc ion has full d orbital and doesn't meet the definition either. Thus we can see कि 3d10 4s2 zinc की फॉर्म में भी दोनों ऑर्बिटल कंप्लीट है. जिंक कटायन जब बन गया तब भी ये 3d10 है. That is why it is not considered as transition metal. You have already come across the fact that when the periodic table is being built, the 4s orbital is filled before the 3d orbital. This is because before filling orbital, 4s orbital have a lower energy than 3d orbital. However, once the electrons are actually in their orbitals, the energy order changes. And in all the chemistry of transition elements, the 4s orbital behave as the outermost highest energy orbital. Transition metal ions. The reverse order of 3d and 4s orbital only applies to building the atom up in the first place. In all other aspects, you treat the 4s electron as being the outer electrons. When D block elements form ions, the 4s electron are lost first. To write the electronic structure of cobalt 2+, now you can see cobalt in ground state You can see the electronic configuration argon 3d7 4s2. When it forms CO2 plus, it is argon 3d7. The 2 plus ion is formed by the loss of the 2 4s electron. Similarly, if we write the electronic configuration V3 plus, vanadium 3 plus ion, तो वेनेडियम का ग्राउंड स्टेट में जो कॉन्फ़िगरेशन है आर्गन 3d3 4s2. In 3 plus state argon 3d2, the 4s electrons are lost first, followed by one of the 3d electrons. To write the electronic structure of Cr3 plus, suppose आपने chromium 3 plus का structure लिखना है. क्रोमियम ग्राउंड स्टेट में कॉन्फ़िगरेशन क्या हो जाएगा 1s2 2s2 2p6 3s2 3p6 3d5 4s1. But when you will write chromium 3 plus, the electron first 4s electron 4s will lose electron first, followed by the 2 of the 3d electrons. That is why the configuration is 1s2 2s2 2p6 3s2 3p6 3d3. Now in the same way, if we write the electronic structure of Zn2 plus, you can see the configuration in Zn2 plus, the last 3d electron is 3d10. 2 electron lost from 4s. Similarly, if we write the electronic structure of Fe3 plus, in ground state, it has configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. But when you write Fe3 plus, then 2 electron first lost from 4s, after that from 3d. The rule is quite simple. Take the 4s electron off first and then as many 3d electrons as necessary to produce the correct positive charge. Variable oxidation state. This is one of the property of transition elements. One of the key feature of transition element chemistry, because they show the wide range of oxidation states. Iron has two common oxidation state, +2 and +3. For example, +2 and +3. It also has less common +6 oxidation state in ferrate 6 ion FeO4 2-. Manganese has a wide range of oxidation state in its compound. For example, Mn2 plus Mn2O3 +3 state है यहाँ पे. In MnO2 it is +4. In MnO4 2- it is +6. In MnO4- it is +7. Now why transition elements show variable oxidation state? When a metal form an ionic compound, the formula of the compound produced depend on the energies of the process. On the whole, the compound formed is the one in which most energy is released. The more energy released, the more stable the compound. There are several energy terms to think about, but the key ones are the amount of energy released to ionize the metal, the sum of the various ionization energy. The amount of energy released when the compound forms. This will either be lattice enthalpy if you are thinking about solids, or the hydration enthalpy of the ions if you are thinking about solutions. The more highly charged the ion, the more electrons you have to remove and the more ionization energy you will have to provide. Here are the changes in the electronic structure of iron to make +2 or the +3 ion. Now you can see this structure. The 4s orbital and 3d orbitals have very similar energy. There is not a huge jump in the amount of energy you need to remove the third electron compared with the first and second. Now you can see the second and third ionization enthalpy. Difference in the second and third ionization enthalpy of iron and calcium. There is an increase in ionization energy as you take more electrons of an atom because you have the same number of protons attracting fewer electrons. Now, formation of complex ion. As we know, transition elements form complex ion. What is a complex ion? A complex ion has a metal ion at its center with a number of other molecules or ions surrounding it. These can be considered to be attached to the central ion by coordinate bonds. The molecules or ions surrounding the central metal ion are called ligands. Simple ligands include water, ammonia, and chloride ions or any halide ions. What all these have got in common is active lone pair of electrons in the outer energy level. These are used to form coordinate bond with the metal ion. Some example of complex ion formed by the transition elements. Just we can have a look. Other metals also form complex ion. These are transition metals, however, form a very wide range of complex ions. Like you can see aluminium, we are going to look in detail at the bonding in the complex ion formed when water molecules attach themselves to an aluminium ion to give this complex ion. Start by thinking about the structure of a naked aluminium ion before the water molecule bond to it. Aluminium has the electronic configuration or the structure we can see. When it forms Al3 plus ion, it loses 3 level electrons to leave 1s2, 2s2, 2p6. Now, there are 6 empty orbitals we can see. Only one lone pair is shown on each water molecule. The other lone pair is pointing away from the aluminium and so is not involved in the bonding. The resulting ion look like this. You can see the electronic structure and the geometry of complex. Now, because of the movement of electron towards the center of the ion, the 3 plus charge is no longer located entirely on the aluminium, but is now spread over the whole of the ion. Because of aluminium is forming 6 bonds, the coordination number of the aluminium is said to be 6. The coordination number of a complex ion count the number of the coordinate bond being formed by the metal ion at its center. In a simple case like this, that obviously also count the number of ligands, but that is not necessarily so, as you will see later. Some ligands can form more than one coordinate bond with the metal ion. Here is an example of iron. It is also forming complex ion with water. Now we can see the structure. Looking at this, the electrons in the boxes at the bonding level. Now we can see that water has donated lone pair in 3D 4s and 4p orbital. This is the geometry of the complex. CuCl4 is another example of the formation of a complex ion with a negative charge. Here you can see the orbital diagram. This is how they form complex ion. Thank you. Next we'll discuss in next class. Thank you, children.